like, share, subscribe.
Hey y'all, welcome back. So today we're going to start a new unit over polynomial functions. So first, let's define what a polynomial function is. So a polynomial function is a function that involves non-negative integer powers or only positive integer exponents of a variable in an equation. You've dealt with many polynomial functions as you've gone through Algebra 1 and Algebra 2, and even into pre-calculus so far a little bit. Some common ones that you've dealt with already are, for instance, a linear function or a quadratic function. Now this equation that's written right here looks a little crazy, right? Like this looks a little bit more complicated than what's really going on. But basically what this is saying is if you have a polynomial, you can write it in this format. And because polynomials can be of any degree, meaning like their exponents could be as high as you want them to be, it's really not reasonable to write like a general form of a polynomial because we don't really know how many terms are going to be, and this is about the best we can do. So this a sub 0 over here, this would be like your constant, and then for every term after that, like moving towards the left, each exponent on the variable just increases by 1 if you write this in standard form. So notice how this is like x to the first, x squared, x cubed, all the way up to x to the n, where n is what we call the degree of the polynomial. So polynomials are typically classified based on their degree, and we're going to look a little bit more closely at these polynomials' degrees to help us sketch some of these functions. So just to kind of go over a couple of examples here, a constant function is one where you don't actually have any variables in it, so you might just have like f of x equals 2, right, where it's just y equals 2. If you don't have a variable, then really all you have is this last term, this a sub 0, which is the constant, and every other coefficient would be 0 in front of that. A linear function is one that has a degree of 1. So you might have something like 2x plus 3. This is an equation that's in slope-intercept form, and you worked with linear functions a lot in Algebra 1 and even probably pretty extensively in Algebra 2 as well. Quadratic functions are ones that have a degree 2. So the highest exponent on a quadratic function is 2. So we have something like, I don't know, and I'm just making these up as we go along, 4x squared plus 2x plus 1 or something like that. And then a cubic is one that has a degree 3 and so on. So you can kind of see how, depending on whatever the highest exponent is of these polynomials, that's how we're going to classify these. Now you might not see every individual term after the leading term, and that's just because that those coefficients are 0. So you don't necessarily need to write a constant, or like in this case I skipped over the squared or the quadratic term. And that's okay. We're still going to classify this as cubic based on whatever the highest exponent is. So if there is no variable, this is a degree 0, meaning like it's x to the 0th. This is degree 1, degree 2, degree 3. We've also seen some functions this year that are not polynomial functions. Most notably, the one that we've dealt with the most this year is our sinusoidal function. So like sine of x is not going to be a polynomial function. Some other non-examples, one that's maybe not as obvious, is if one of the exponents is negative. So if I have something like this is not considered a polynomial function. If you've got like a fraction, I guess this is kind of the same thing here, but if you have a function that's written like this, where even though we have a positive exponent here, we've got 1 over, and so really you would write this as like 2x in parentheses to the, or I guess 1/2 x to the negative 3. So no negative exponents are allowed. Some other ones that are just not polynomial functions are like if you have absolute value, or if one of your terms has a fractional exponent, so like the square root of x or x to the 1/2, we're not going to consider that a polynomial function either. So the key here is this exponent needs to be positive and it needs to be an integer. Okay, so if n is a non-negative, meaning positive, or 0 integer, then we will have a polynomial function. So there's quite a bit more. You know, we just got done talking about logarithms, so like exponential functions or logarithmic functions. Both of these would be non-examples of polynomials. These are all different kinds of functions. So what we're going to focus on today is learning how to do sketches of these polynomial functions. And one of the key ideas that we need to understand before we can start to sketch any of these functions is the end behavior of these graphs. So when I talk about end behavior, what I'm talking about is what's going on at the end of the graphs. In other words, like as x goes all the way to the left, and as x goes all the way to the right, what's happening to the graph of the function? Is it going up? Is it going down? Is it approaching a certain number? And so on. So with polynomial functions, we're going to look at two individual items in the equation to determine a polynomial's end behavior. In other words, like what's going on as x approaches positive or negative infinity. Now, before we get into how to decide what's happening in the graph, I just want to clarify a little bit of notation and just like how we're going to answer these questions. So this is sometimes called the infinity notation for describing end behavior. But let's say we're talking about what's going on the left-hand side of the function. In other words, as x approaches negative infinity. The way we're going to describe that behavior is we're going to say something like this. As x approaches negative infinity, f of x approaches what? Either it's going to approach infinity or negative infinity. In other functions, not polynomial functions, but other functions, we've seen sometimes we have a horizontal asymptote, in which case the function would approach a certain number, and we'll look at those when we talk about rational functions in the next unit. But for polynomial functions specifically, the function is only going to go up or it's going to go down. Okay, it's not going to approach a single value. So this will be either plus or minus infinity. Now you can see that this is kind of a lot to write, and so we have a more symbolic way of stating the same statement. So as we say, as x approaches negative infinity, instead of writing approaches, we are going to write a little right arrow. And let me see if I can find one for you real quick. All right, here we go. So pulled one up, and so yeah, it'll look like something like this. And obviously, we're not going to write the word negative. We'll just put a minus there, or to make this a little, I might even put a bigger little minus. And then infinity has its own little sideways symbol. So as x approaches negative infinity, in other words, as the function goes to the left, we want to know, is f of x going up or down? Is it going to approach positive or negative infinity? Again, the symbol we use for approach is going to be this, and then plus or minus, we just write like this. Oh, nope, not another arrow there. We want plus or minus. There we go. And then finally infinity. So it's going to be written kind of like this, right? So, but we're not going to actually write plus or minus. We want to decide, hey, is it plus or is it minus? So if it's plus, we'll just write infinity. Okay, we don't need to actually write the plus. And if it's minus, we'll actually write the minus. And so what this is saying is, as x approaches the left, okay, so the way we're interpreting this is on the left-hand side, either the function is going up or it's going down. Okay, so if it's approaching positive infinity, that means that it's going up, and if it's approaching negative infinity, that means it's going down. Okay, to the left-hand side. And we'll go through like how to determine that on the next slide, but I just want to make sure that we get the really like the grammar or the way we're going to answer these questions correct. Now, as we approach, as x approaches infinity, so as the graph goes to the right-hand side, we will make a similar statement to describe the end behavior. It's either going to go up or down, but the way we'll say it is instead of saying as x approaches negative infinity, we'll say it as x approaches positive infinity. So either the graph is going to go up or down, just like with the last one. So we'll also say, hey, if f of x is approaching positive infinity, that means it's going up, and if it's approaching negative infinity, that means it's going down. So this is how we're going to describe end behavior, and this is going to be pretty common notation that we'll use for the rest of the year, and even going into calculus, you'll use this infinity notation to describe how a function, like what is a function approaching. So let's go over how we're actually going to decide what the end behavior is. Okay, so there's two things that you need to look at on the polynomial to decide what the end behavior is going to be. You need to look at the degree of the polynomial, which is the highest exponent, the largest exponent. Okay, and we want to look at the leading coefficient. Okay, so the leading coefficient is, if your polynomial is in standard form, it'll be the number right at the very beginning. Looks like I'm going to have to zoom out a little bit to make all this fit here. So first we'll look at the degree, and we will try to decide, is the degree going to be even or is it going to be odd? Okay, in other words, like a quadratic would have an even degree, whereas a cubic would have an odd degree. Okay, so depending if it's even or odd, something different is going to happen. And then we'll also look at the leading coefficient. And what we're looking at for the leading coefficient is whether or not it is positive or negative. So if the degree is even and the leading coefficient is positive, so an example of that would be, let's see, I'm going to write this out here. So an example would be something like f of x or y equals x squared, for instance. Then the left-hand behavior is going to be going up and the right-hand behavior is going to go up. So like if I were to sketch out a little, a quick sketch of the parent quadratic function here, it would look like this, right? And so what we can see is that the function is going up both to the left and to the right. So the way we would describe the end behavior is as x approaches the left, we're going up, y is going up, and as x approaches the right, y is also going up. So the way we'll describe that is using this infinity notation. So we would say as x approaches negative infinity, y or f of x is going to approach positive infinity, and the same thing is going to be true towards the right-hand side. Okay? So this would be how we describe the end behavior, and then the rest of this that I have over here is just like a very simple example to kind of help you remember what's going to happen. Hopefully you know what the parent quadratic function looks like. Now I do want to I want to make sure that this is very clear. So what these two statements are basically saying is, as x goes to the left, y goes up, okay? So, and also as x goes to the right, y goes up. So this is the way that you would typically write it with, like I said, this infinity notation. But if you're just trying to understand what's going on, maybe this can kind of make it a little bit more clear. Okay, I just want to make sure I got enough space here. Okay, so that's what happens if the degree is even and the leading coefficient is positive. Now let's say the degree is even, but the leading coefficient is negative. So in other words, we've got a situation where, let's see here. We got a situation where, like, let's say we have, like, instead of x squared, we have, like, negative x squared, right? So hopefully you know what that's going to do to the graph, just from your experience in Algebra 1 and Algebra 2. If you've got a negative sign out here, where it's like negative x squared, what that causes is a reflection over the x-axis. And so instead of opening up, you're going to be opening downwards. Okay, so it'll kind of do something like this, right? And so as we approach the left and the right, the function is going to be going downwards. So as x approaches negative infinity, f of x should approach negative infinity, and as x approaches positive infinity, y will be approaching negative infinity as well. So in other words, as x goes to the left, y goes down, and as x goes to the right, y goes down. And it's not really fitting very well, so I think what I might do is just do something maybe like this. Make that a little clearer. Okay, so what I want to point out here, though, that is when your degree is even, notice that both behaviors on the left and the right are going the same direction, right? They're either both going up or both going down. And depending on what the leading coefficient is, that will tell you whether or not they're both going up or both going down. There we go. Okay, that's looking a little better. Okay, so what happens then when it's odd? Okay, so let's say, like, for example, we've got like y equals x cubed, right? Or y equals x, or y equals x to the fifth. Then instead of the end behaviors going in the same direction, like both going up or both going down, they're going to be going in opposite directions. So one will be going up and one will be going down. So if the degree is odd, like let's say, for instance, we have something like x cubed, so instead of x squared, let's see, let's get rid of this. So x cubed, and you may not be as familiar with x cubed because you probably just haven't dealt with it as much as x squared. But basically what happens is it does go down to the left and it kind of snakes into the, well, for lack of a better phrase, it kind of like bends at the x-axis, but at the origin rather. And it does pass through the origin. It does something like this, okay? It's a very rough sketch here, but the point is, as x approaches the left, as x approaches negative infinity, then f of x is going to approach negative infinity. And so basically what that means is as x goes to the left, y goes down. Okay, and as x goes to the right, as x approaches positive infinity, f of x goes up, y goes up. So if the degree is odd, then I just want you to see how the direction that the function is going in opposite directions rather than the same direction. Now if I make the leading coefficient negative, just like with this other example over here, what it does is just flip the graph over the x-axis, and so we'll have the opposite behavior, right? So to the left will go up, and to the right will go down. But it'll be, we'll describe it very similarly here. So let's say our example here is negative x cubed, right? So we've got a negative leading coefficient and then odd degree. So this function is going to be flipped, and as we go to the left, the function's going up, and as we go to the right, the function's going down. Okay, that looks pretty bad. Drawing these with the mouse is never ends well. Okay, so as x approaches negative infinity, f of x is approaching positive infinity. Okay, so y is going up to the left, and to the right, it's going downwards. So as x goes to the right, y goes down. So when I ask you to describe the end behavior, you don't have to necessarily give this second statement. This is really just me in the notes trying to describe what this means. The only thing you need to write is whether or not f of x is approaching positive or negative infinity. Just remember, positive infinity up, negative infinity down for f of x. For x, negative infinity is to the left, positive infinity is to the right. So what's interesting is no matter how complicated your polynomial gets, so let's say your polynomial kind of looks more like this, where you've got like, 5 or 6 terms, what's kind of cool is to know the end behavior, the only thing that is really going to affect that is the leading term. And specifically, the degree, whether or not it's even or odd, and the leading coefficient, whether or not it's positive or negative. So all of your polynomial functions are going to fall into one of these 4 categories. And this doesn't tell us what the whole graph is going to look like. It just tells us what's going on in the long term. So like at the very ends of the graph, are we increasing or are we decreasing? One other thing we need to discuss before we really start getting into the sketches is this idea of multiplicity. Okay, so when you solve for the zeros of a function by setting the equation equal to 0 and solving for x, sometimes you get a repeated zero, meaning like, for instance, if I have an equation that, let's say I factor it, and I get something like y equals x plus 2 times x plus 2, for instance. So I had a polynomial and I factored it and it turned into this. If I want to find the zeros by setting this equal to 0, what I'm going to get is x equals -2 and x equals -2. So whenever that happens, where you get the same root more than once, we say that that root has multiplicity equal to how many times it's repeated. So like in this case, we would say something like x equals -2 with a multiplicity of 2, okay, because there's 2 of them. So depending on what the multiplicity of the roots are will determine how the graph crosses the x-axis. Okay, so if you just have like a single root, so let's say we just had like x, if this was x minus 2, x plus 2, we would get 2 separate solutions here. We would get 2 and -2. So these would each be single roots. And the way that a graph will cross the x-axis at a just simply like a single root. So let's say here's the x-axis, right? We know that the root is going to pass through the x-axis. That's what a 0 is. But if it's a single root, then the graph is just going to simply pass through, okay, almost linearly. So basically, there's not going to be any change in the slope or a dramatic change in the slope as we approach the x-axis. It's just going to pass right through. So we can just sort of like sketch without, doing any extra curvature or anything. So I usually describe this as just passing through the x-axis. Now, if the multiplicity is even, so like if I had that situation where I have 2 roots that are both the same, so if I have like x minus 2 twice, I would just get x equals 2 with a multiplicity of 2. This happens, like for instance, if I scroll back up here on like x squared, right? Like so this has x equals 0 twice. Then what happens, notice we don't just pass through the x-axis, instead we bounce off of it, okay, and go back in the other direction. So if you have an even multiplicity, and this is true like not just for quadratics, but for quartics and 6th degrees and so on, now the root needs to be repeated that many times, but if it is, then you will bounce off of the x-axis. So let's say here's the x-axis. If you have a multiplicity like 2 or 4 or 6, then what's going to happen is we will like bounce. We'll hit the x-axis, and then the function will kind of go back in the direction that it started in. Okay, so it'll have like the same sign. It'll be like, let's say, above the x-axis before the x-intercept, and then above the x-axis afterwards. And the same could be true for whether, if you're below the x-axis, you would come up, hit the x-axis, and bounce off. And I call this a bounce. So this, I would say, bounces off the x-axis. Now, if we have an odd multiplicity, now I'm not going to include 1 in this. If you just have the single root, it's just going to pass through like this. But let's say we have like a triple root. Okay, so in other words, we have like something with a multiplicity of 3. Then what we get is this bending behavior at the x-axis. And a good example here is going back to this x cubed, where this would have a 0 of, well, 0, but it's repeated 3 times. So we get x equals 0, x equals 0, x equals 0. And so this would have a multiplicity of 3. And notice how the graph kind of like bends through or kind of snakes through the x-axis here, where it looks like it wants to bend, but then it's like changes its mind at the last minute and then kind of goes back in the direction that it was trying to go in the first place. So when we sketch this out, the graph is going to, let's see, so if this is our x-axis, as the function approaches the x-axis, then we have this sort of bending behavior where it looks like it's almost going to bounce off like this, but no, it decides to continue through. Okay, so this would be, here's a single root, an even multiplicity, and an odd multiplicity. And the way that I'll describe this as we go through problems is that this is going to bend through. So it bends through the x-axis. Okay, so with a single root, just passes through, and we don't have to like change the curvature as we're sketching. On an even multiplicity, we want to bounce off and go back in the same direction we started in. And then for an odd multiplicity, we sort of bend through the x-axis, although we do pass through it. So let's use all of that, okay, to start learning how to sketch polynomials. And when you're sketching these, there's sort of a minimum amount of information you need to convey with your sketch. You need to find the x-intercepts using usually factoring. We need to find the y-intercept, and I'll show you how to do that. And then we also need to consider the end behavior. And between those three things, we can usually get a reasonable sketch of the graph. Now, we're not looking for like a ton of accuracy here in terms of like sketching it to scale or anything like that. As long as we label the intercepts and we are correct about the end behavior, then that sketch will be good enough. We're just looking for the general behavior so that we can kind of get an idea of what the graph would look like, and not so much worried about making sure every little point is exactly to scale with the rest of them. So let's take a look at this first one. Y equals 4x to the fourth minus 12x squared. So we're going to be looking at three things. We're going to be looking at the end behavior, we're going to look for the x-intercepts, and we're going to find the y-intercept. So the first thing that I like to find, just because I find that it's pretty easy to compute, is the y-intercept. So first we're going to find the y-intercept. And to find the y-intercept, we're going to substitute. So the y-intercept is the point where our graph crosses the y-axis. And so any point that's along the y-axis is going to have an x value of 0. So to find the y-intercept, we are going to substitute 0 in for x and evaluate. So that's it. There's nothing to solve or anything like that. You just basically plug in 0 and calculate it out. So to find the y-intercept, I'm going to plug in 0 here for x. So I get 4 times 0 to the fourth minus 12 times 0 squared, and that's just going to equal 0. Okay, so we've got our y-intercept is 0. So I'm going to just make a little point here, or I'm just going to type in 0, comma 0. Or maybe I'll just write, yeah, I guess I will leave it like that. Come on, there we go. Okay, so that's the y-intercept. Next, we need to find the x-intercepts. Okay, we can actually plot this y-intercept already. So I'm going to go ahead and do that. Just going to be right here. Okay, so for the x-intercepts, this one takes a little bit more work here. I'm not sure how many we'll have. The fundamental theorem of algebra is going to guarantee us 4 roots, but that doesn't guarantee, whether or not it's possible that they might be repeated. So we might only get like 1 x-intercept, or sometimes you get none. So let's see what happens here. Whoa, why is that so? There we go. Okay, so to find the x-intercepts, what we're going to do is we are going to substitute 0 in for f of x, or y, depending on how the equation is written, and solve for x. And usually you'll have to use factoring. Sometimes you got to use quadratic formula. Sometimes if it's linear, you don't have to do any of those things. And you can just use your properties of equality. But let's see how this particular one's going to play out here. We've got 0 equals 4x to the fourth minus 12x squared. Okay, so to solve this, I'm going to start by factoring out a GCF, which it looks like is going to be 4x squared. So I'll have 0 equals 4x squared times x squared minus 3. Okay, so I've got my factors, and it might not look like it exactly, but I actually have a total of, here I really only have written the factors, like there's 2 factors here, but I'm still guaranteed 4 roots. This x squared is going to have 2, and then this will have 2. Now if I solve this one, what I get is 4x squared equal to 0. And then the other factor, when I set it equal to 0, I'm going to have x squared minus 3 equals 0. Now to solve the one on the left, I'm going to divide both sides by 4, and then take the square root of each side. And what I really end up with here is x equals plus or minus 0. And so I actually end up getting a repeated root here. I get a root of 0, but it has a multiplicity of 2. Now I know it's got a multiplicity of 2 because the degree, so I can just write it like this, multiplicity 2. Because this is a quadratic here, right? So this is like 4 times x times x. So either one of those two x's could equal 0. Now over here, I'm going to add 3 to both sides and then take the square root. So I'm going to end up with x equals plus or minus root 3. So let's see, plus or minus square root of 3. Now these are both single roots, and we can double check our fundamental theorem of algebra, right? It says that we're going to get 4 roots, and I have accounted for all 4 roots. I've got 1, 2, 3, and 4. Now this 0 we should have already known about because we found the y-intercept, but the other ones we'll go ahead and plot. So before I do that, I'm going to write out all my x-intercepts. So I have the one at 0, 0, and that is going to be a duplicate. So we are going to have like this bouncing behavior there. And then the other one will be root 3 comma 0, and then we have the second one at negative root 3 comma 0. All right, so there's our 3 x-intercepts. Okay, so let's go ahead and plot those other 2 x-intercepts, and then we'll talk about the end behavior and how to sort of finish off the graph. So the other 2 x-intercepts here are going to be at plus or minus root 3. So again, the scaling here is not important. Just make sure, if these are plus or minus root 3, just try to get them to look like the same distance away from the 0 as you can. I'm not like labeling anything outside of that. So like here, I'll just say that that's like negative root 3, and here's root 3. And that's all the detail you need, really. Okay, so the last thing we need to find is the end behavior. So let me scroll down a little bit to make this fit. Okay, so for the end behavior, we are looking at the leading term, and the leading term here is 4x squared. So let me just sort of highlight that. This is the leading term, right, 4x squared. And so what you need to examine is both the degree and the leading coefficient to determine the end behavior. So since the degree is even and the leading coefficient is positive, we can say that the behavior is going to be up and up. In other words, as x approaches plus or minus infinity, f of x is approaching infinity. Did I misspell that? Coefficient, I guess I did. Okay, so the degree is even, the leading coefficient's even, so the way we're going to describe, or is positive rather, so we're going to describe it using this, notation here. So we're going to say As x approaches negative infinity, f of x approaches positive infinity. As x approaches positive infinity, f of x is also approaching positive infinity. So one way to kind of think about this is to the left, it's going up, right? To the left, oh, that's a terrible arrow there. It's going up, and to the right, it's going up. Okay? Now how that helps us to sketch out the graph is you want to go to basically like the furthest most x-intercepts that are, the most to the left and the most to the right, and then use these arrows to indicate like which way it's going. So like I know it's going up and up to the left and to the right. So I'm going to go up this direction. Oh, I don't want to curve back, but I want to go up this way, and I want to go up this way. Okay? So that tells me the long-term end behavior. And then for what's going on like in between all the x-intercepts, that's where we use the multiplicity. Okay? So like this one is going to have a multiplicity of 2. Okay? So what happens at 0, 0 is we have a bounce. Okay? We've got a bounce. And since these are all, the plus or minus root 3 are just individual roots, they're just single roots, we're just going to pass through. So these are just going to be, usually will describe these as like bounce, pass, or bend. So this is a bounce, this is a pass through, and so is the last one. Okay, so as I'm sketching my graph here, I'm going to pass through without like changing like sort of the momentum or the slope significantly. As I pass through here, then I need to bounce off the root of the x-intercept 0, 0, and then I pass through the x-axis over here. And so here's our sketch, we're done. Okay, so just to kind of go through that, we first found the y-intercept, then we found the x-intercepts, and then we determined the end behavior to really kind of put the graph together. And that's it for this first example. Looks like I lost a little bit of my curve here. So let's try to like put that back in there. And there you go. So there's your sketch. So that's the first one. I'll move through the next few a little faster, but we'll be basically doing the same thing here. We're going to find the y-intercept. We're going to find the x-intercepts. We're going to look at the end behavior, and then just kind of put all the pieces together for the curve itself. So what I might do here is, so I don't have to retype all this, is just copy and paste this for each of the problems and then just adjust as we need to go. So here's the next one, x cubed minus x. And I'm just going to move this over here and just kind of delete what we don't need. So here we have x cubed minus x. So we'll find the y-intercept by plugging in 0 for x. So that'd be 0 cubed minus 0, which is just 0. So just like with the last one, we do get a y-intercept at 0. So we can kind of expect that that's also going to be an x-intercept too, since it is crossing at the origin. We'll get to that once we get to that. Okay, so there's our y-intercept. Now to find the x-intercepts, we want to substitute 0 in for y and then solve for x. So here we'll have 0 equals x cubed minus x. And here we can factor out a GCF of x, and so we get x times x squared minus 1. And we'll set both of those equal to 0 and solve them individually. The x is just going to end up being like, x equals 0. So we do get a single root there, which we were already expecting. And then for the other one, we've got x squared minus 1 equals 0. So to solve for x there, we would add 1 to both sides and then take the square root of 1, and we'll get plus or minus, if I can get in there we go. We get plus or minus 1. So these are all going to be single roots. This is a cubic function, so we should expect 3 of them. So we get 0, 0, we get 1, 0, and we get negative 1, 0, and they're all individual. They're just single roots here. So let me go ahead and plot the 1 and the negative 1. You know, again, these do not have to be like perfectly spaced. You just want to do the best you can here. And I'll label this as 1 and negative 1. Okay, so those are my x-intercepts. And then the end behavior, let's look at the degree. The degree is 3, which is odd. And the leading coefficient is positive, because it is just 1. So if we go back up here, until you can kind of memorize this, when the leading coefficient is positive and the degree is odd, our behavior is going to be down, up. Okay, down to the left, up to the right. So down to the left means that as x approaches negative infinity, f of x is going to approach negative infinity. Oops, I'm on the wrong one. My bad. There we go. And then as x approaches positive infinity, y will also will continue to go to positive infinity there. So as we sketch this, we know that the end behavior is going to be down, up. So just to kind of give us a little bit of an indication here of what's happening. So down, up. So to the left, it's going down, and to the right, it's going up. And each one of these zeros are just single roots. So we don't have to bounce, we don't have to bend. We're just going to pass through each one. So we're going to pass through this one, and this one. They're all going to be pass-throughs. So it looks something like this. Okay, and just to kind of formalize this, here's a pass. These are all going to be pass-throughs. Okay, so that's this second example. We're gonna, I think, do 2 more, or is it 1 more? Yeah, 2 more, and then there's one other thing I want to show you all. Okay, so for this next one, you'll notice that this is not written in standard form, and that's okay. It's not the end of the world. I'll show you how to come up with that leading term down here when we need it. But for right now, it's actually going to be nice if this is already factored out, especially for when we're finding the x-intercepts. So first, let's do the y-intercept. We'll plug in 0 everywhere we see x. So we get 0 plus 3 times 0 minus 3 times 0 minus 7. And that first factor, that 0 plus 3, is squared. So what we get here is 0 plus 3 squared. So that would be 9 times negative 3 times negative 7. And if my napkin math is right here, let's just go ahead and type this in. I'm not sure exactly what that's going to be. 189, I think, might be right, but let's double check. So, yeah, we've got 3 squared times negative 3 times negative 7. Okay, so that's good. Yeah, it is 189. Okay, cool. So, yeah, we get 189 as our y-intercept. And again, like, don't worry about the scaling here, okay? We just know we've got a positive y-intercept, so I'm just going to throw that somewhere up here, okay? And as long as I label it, I'll be safe. So I will label this 189. Okay. Now it says, let's see here. What do we need next? We need the x-intercepts. So to find the x-intercepts, we're going to set the equation equal to 0. And then solve it. So let's see, can I make this a little bigger? I don't know why this is giving me so much trouble. Sorry about the delay here. I really do not know what the deal is, why this is not letting me make it bigger. Sorry, you guys are like, move on with it. We don't care. Okay, so yeah, let's just move on. So although it is going to kind of bug me. Maybe I'll just make a new one. There we go. That will work. Okay, so to find the x-intercepts, what in the world? Okay, I'm kind of struggling there. Not sure what the deal is. Maybe I could just drag it over. Oh, it did let me drag it over a little bit, but it's very... Okay, there we go. Okay. I don't know why that was bugging me so much. Okay, so to find the x-intercepts, we want to substitute 0 in for y and then solve for x. So the good news is, check this out, it's already factored. We don't have to factor it out, so finding the zeros here should be pretty easy. Okay, so we don't really need this next step because we already have it factored, but we do need to set each factor equal to 0. So we've got x plus 3 squared equals 0. And really that's x plus 3 times x plus 3. So this is going to result in a root that has a multiplicity of 2. So just be ready for that. We also have x minus 3 equals 0, and we have x minus 7 equals 0. Wow, this is like really lagging on me. What is even happening here? X minus 7 equals 0. So we'll solve each one of these, which won't take much. Like if we take the square root of 0, we get plus or minus 0, which is just 0 and 0. Minus 3 would be negative 3. And again, this does have a multiplicity of 2. So that's going to be important when we go and sketch the graph. So for the next one, we get x equals 3. That's just a single root, so no multiplicity there. And then finally, we get x equals 7 as our last one. And that is also going to be a single root. So we do get 3 x-intercepts, one of which is coming from a double root, so that'll affect how we pass through the graph, or how we go through the x-axis. So we've got negative 3, comma 0. We've got 3, comma 0. And we have 7, comma 0. So the negative 3, which has a multiplicity of 2, that's going to be a bounce. The 3, comma 0, that's just going to be a pass through. And then same thing with 7. I haven't seen one with an odd multiplicity yet. Maybe the next one. Hopefully the next one. I want to show you how that works too. Okay, so for the end behavior, we're looking at the leading term, which is not like super obvious here because it's not in standard form. So to find the leading term here, if it's not in standard form already, we just need to multiply the first term out, okay? So to find the leading term, we're going to do x squared, okay, because this thing is squared, so it's like x plus 3 times x plus 3. So x squared, basically we're just going to multiply, just to kind of keep this simple for you, multiply the first term of each factor. So x times x would be x squared, times x would be 1x to the 4th. Okay, so that would be what the leading term would be. That degree is even, so we know that the end behavior is going to go the same direction to the left and to the right, and the leading coefficient is positive. So since the degree is even and the leading coefficient is positive, we're going to be approaching positive infinity on both sides, kind of like the first example where we went up and up. So yeah, we want to go up and up on the sort of outer portion of the graph. So I'm going to plot these 3 x-intercepts. So here's where I'm going to estimate is negative 3. Again, don't worry about the scaling here. Just make sure everything's like in order. And then, see, why does it do that? I don't understand that. So here's negative 3. Here's positive 3. And then positive 7 would be like way out here. So here's negative 3. 3, and 7. Okay, so now that we have all of our intercepts labeled, we can go ahead and start sketching the graph out. I like to start with the end behavior, and it should be going up in both directions. I don't know why I drew a downward arrow here. I'm catching that. Yeah, it should be going up to the left and to the right. So from these outer x-intercepts, I'm going to go up and up. Okay? Now for each x-intercept, I'm going to decide like what's going on there. Am I going to bounce off? Am I going to pass through? Am I going to bend? And I've already made those decisions over here. So I'm going to kind of follow this. So I'm going to bounce off of x equals -3, which kind of makes sense because I do need to go up and I need to hit this y-intercept that's way up here. Okay? And then I come down and this is going to be a pass through and then finally a pass through. So the graph's going to look roughly like this. Now this is not to scale. Okay, if you put this in your calculator, it's going to look way more stretched. Because look at what's going on here. -3 and 3 and then 189. So really like this is going to shoot up almost, it's going to look vertical on your calculator unless you mess with the window. But if you scale it down, if you scale the y-axis down, it should look somewhat like this. All right, so there's that one. So I've got one more graph to show you, and then we will, there's one other kind of problem I want to show you as well, and then that'll be it for today. For this one, let's start with the y-intercept. So we're going to plug in 0 everywhere we see an x, and hopefully you'll catch on here that if all of the terms have an x, then you don't really have to calculate anything. You know it's just going to be 0. But I'll go ahead and just type it in here so you can kind of see it in action. So in each of these terms, I'm multiplying by a 0, so the whole thing is just going to equal 0. Nothing too interesting going on there. Oops. Now, I do need to factor this. Why isn't it typing 0 here? There we go. This lag is killing me. I don't know what's going on today. Okay, so for the x-intercepts, we're going to set the equation equal to 0. We're going to solve it. So -6x to the 5th plus 12x to the 4th plus 90x cubed. So I'm going to factor out, I think all these are divisible by 6, so I'm actually going to factor out a -6x to the 3rd and be left with x squared minus 2x minus 15. And I need to factor that out a little bit further, so I'm going to move all this down, give myself a little bit more room here. So I will have, let's get back to the equation. Come on. So we got x equals -6x cubed, and then this should be factorable. Okay, two numbers that multiply to give me -15 and add up to -2 would be -5 and +3. So I'd have x minus 5 and x plus 3. So now I can get all my zeros. Now the first one would be -6x cubed. Not z, 6x cubed equals 0. This is going to be a triple root, okay, because it's x squared cubed. It's x times x times x. So what I get here is x equals 0, which we kind of already knew was going to happen. But this is the first time we've seen one with a multiplicity higher than 2. So this one will have multiplicity 3. And what that's going to do to the graph is it's going to cause a bend through the x-axis. So yeah, that's got multiplicity 3. The next 0 we'll get from x minus 5 equals 0. And then, so x is going to be 5. And then the last one will be x plus 3 equals 0. And so from there we have x equals -3. So these are our 3 x-intercepts, one of which has a multiplicity of 3. So we've got 0, 0, and that's going to be a bend. We've got 5, 0 is going to be a pass-through, and then -3, 0 is going to be a pass-through as well. So we got a bend, a pass-through, meaning that it just goes right through it, almost linearly, and then we get another one, another single root. Okay, so for the end behavior, we see that the degree is odd and the leading coefficient is negative. Okay, the degree is, come on, there we go. Nope. This is getting kind of frustrating. I don't know why it's taking so long to do every click. Okay, so the degree is odd, and the leading coefficient is negative. Okay, the leading term that we're looking at here is this one up here, the negative 6x to the fifth. So I'm going to start by plotting all my intercepts. Okay, I've got the one at 0, 0, which is serving as both the y-intercept and that triple root x-intercept. I've got a 0 at negative 3, making these kind of big, and then 1 at 5. I'll go ahead and label these. So negative 3 and 5. So the end behavior is going to be as x approaches negative infinity, f of x is going to, since the degree is odd and the leading coefficient is negative, we're going to go up to the left, and I guess I forgot to put the minus on here. We're going to go down to the right. So yeah, f of x should be going to negative infinity to the right. Okay, so for the sketch, we're going to be going up to the left, down to the right. We're going to kind of bend through 0, 0. So negative 3 is just a straight pass-through, but as we approach the 0 at the origin, we're going to kind of like make like we're going to bounce and then change our mind. Okay, so have a little snaking oh gosh, this is looking terrible. Okay, so let me try that again. We're going to snake through there, okay, and then 5 just a regular old pass-through. So kind of having, it's almost like it goes horizontally here, just for like a split second, and then it's going to continue up. So that's going to be the sketch of this one. Okay, so there's one last problem that I want to show you how to do, and that's kind of how to go backwards from the roots and how to write our equation. So for this last one, we're trying to write the function given the roots. So let me just kind of walk you through this. We are going to write a function, so f of x equals, and then for each root, we're going to include a factor here. So if the root is 2, with a multiplicity of 2, that's like x minus 2 times x minus 2. Okay, but when we multiply that together, you should notice that, hey, the y-intercept is not correct, right? Like if I multiply this together, I get x squared minus 4x plus 4, but I want the y-intercept to be 8. So to accomplish that, what I need to do is multiply the entire function by a factor, like throw in an extra factor. And so you have to figure out, okay, well, 4 times what gives me 8, and that would be 2. So I would need like this extra constant factor of a 2, and that would give me 2x squared minus 8x plus 8, and now I've satisfied both the roots and the y-intercept. But the trick here is to come up with the factors first, multiply them together, and then figure out what the leading coefficient needs to be able to satisfy that y-intercept. So that's, oh, that is not a rectangle. That's it for today, y'all. Y'all have a great day, and I'll see you next time.